Hi everyone, my name is Teja and welcome to this video series on probability for business analytics and machine learning. So in this video, we're gonna extend our discussion about random variables to multiple random variables and the notion of joint probability mass functions. And RVs is a short form for random variables. So what do I mean by joint probability mass function? So this is what I mean. It's probability of x is equal to x and y is equal to y. Okay, so this is a new notation. Okay, I'm introducing, so x and y are two random variables, which means they're functions from the sample space to some numbers. Okay, so this notation can be shortened to probability of x is equal to x comma y is equal to y, or sometimes we will also write probability of x y, where x y is in the subscript bracket x little x little y. And this, as you know, is nothing but this is a probability law. It's called joint probability mass function, and this has to be this is equal in definition to these sets, right? So this is a set of omega in W such that x of omega is equal to x. So this is event A, and the set of omega in omega such that y of omega is equal to little y, right? Think of this as event B. So this is, so event B is a subset of omega, event A is a subset of omega, and just means intersection. So we're just asking for a probability of A intersection B in a very specific way through the definition of random variables. Okay, so this is what joint PMF means. So in this case, what we expect is that the sum over little x and little y of P of x is equal to x and y is equal to little y should sum to 1. Okay, so this is the this is one condition that this derived probability law should satisfy. Also, of course, that P of x is equal to x and y is equal to y should also be greater than or equal to 0. Okay, and so why limit to two random variables? We can also talk about P of x is equal to x, y is equal to y, and z is equal to z. And this can be defined in the very similar way as these guys. Okay, so I will not expand it, but we can do that. We can also think of probability of g, which is a function of multiple random variables x, y, and z. Okay, so just like, I mean, this is in contrast. Remember, in one of the previous videos, we looked at probability of g of x. Okay, for example, I mean, here, for example, it was probability of x square, or probability of ax plus b. Okay, these are all functions, right? Similarly, here we are looking at functions. For example, maybe this function is x times y times z, or maybe this function is x plus y plus z. Okay, it could be any function. So we can also talk about the probability mass function for this derived random variable. So this function is a function of other random variables, 3 random variables in this case, and so it's also a random variable, and so there will be a probability mass function associated with it if x, y, and z are discrete. And we said continuous is almost similar, so I'm gonna delegate it to future lectures, future videos. Okay, so this is these are some examples. So these are some variations of the joint probability mass function that I was talking about. Now, here's the connection to ML. Okay, and in machine learning, there's a bunch of inputs. We typically denote it as x. There's a bunch of outputs. We can denote them as y. In fact, it turns out that we can talk about x as a random variable and y as a random variable. And typically in machine learning, in certain types of machine learning, let's say supervised learning, you're trying to find a function which goes from which takes input x and outputs something which is close to y. Okay, You can think of, for now, think of f as a fixed function, some fixed prediction model. Someone gave it to you, maybe. And think of x and y as a random variable. Then you can have a loss function which measures how close the prediction is from the actual target. So loss is going to be a function of x. Sorry, loss is going to be a function of my prediction and the ground truth, as in the true label or true target. And so loss, so this is a function of two random variables, right? X and y. X first got transformed via f of x, and then this whole thing got transformed by a loss function. Okay, which, this loss function is a number. Okay, so this is just an example of why you would have derived random variables and functions of multiple random variables. Okay. So let me talk about one cool thing. So we looked at the joint probability mass function. So I also want to give show one thing about the expectation. So if I think of expectation of a random variable, a derived random variable, or a function of two random variables, let's say x and y, and the function is just the addition of these two random variables, let's say. So this is the addition of these two random variables. So it turns out that this just evaluates the expectation of x plus expectation of y. Okay, so it does not, so these two are random variables. It does not matter how these two random variables are related to each other, in the sense that in the sample space there's a bunch of omegas, right? Little omegas in the sample space, and these random variables are functions from these little omegas to real numbers or numbers, and it does not matter how they are defined. But irrespective of how they are defined, if there is a function which is an additive function like this, then the expectation of x plus y is just the expectation of x plus expectation of y. Okay, and a cool application, cool application of this is to finding the expectation of the binomial random variable. Okay, so what is the binomial random variable? Let me use x again. So the binomial random variable asks for probability of, so it's easy to describe in terms of this probability definition. It asks for the number of heads k. It's a random variable which says which captures the number of heads that you can land in n trials, and the number of heads can be 0 heads, 1 heads, all the way to n heads, right? So in general, for k heads, we saw this formula. So n choose k, it's just the combination short form times p to the power k times 1 minus p to the power n minus k, right? So this was the probability of the random variable taking a value k, and k can be between 0 to n. Okay. Now I want to find its expectation. So this is a random variable. I know its law, so I can always do the summation, right? I can do sum over x times p of x is equal to k, or actually, yeah, k, and k is equal to 0 to n. Okay, if you do this, then this will give you the expectation of x. But there's a simpler way to derive this, which is to notice that there are n trials. In each trial, there's going to be a heads or a tails. So let me denote an intermediate random variable. Let me use the notation y1 to represent the random variable which takes a value 1 if there is a heads and 0 if there is a tails in the first trial. Similarly, let me denote y2 as a random variable which takes a value 1 if there is heads in the second trial and value 0 if there is a tails in the second trial, all the way to yn. Okay, so I have defined n random variables. These random variables, as the way I described it, they are just Bernoulli. In fact, the Bernoulli with parameter little p is the same parameter that I used here. Okay, little p. Each one is the same, has the same parameter. Now, if you think about it a little bit, this random variable x is nothing but the sum of these random variables, actually. Because if this lands in the first trial, if I land ahead, in the second trial, if I land ahead, then these two values will be 1, and let's say I have tails in the remaining trials, then these random variables will take value 0, for example. So all sorts of sequences are possible. Okay, and that's what this random variable is defined on. This random variable's corresponding sample space was the sequence of all heads and tails, right? Which are n in length. So now if I want to find the expectation of x by the above property, I can think of it as the expectation of y1 plus expectation of y2 plus all the way to expectation of yn. And this turns out to be equal to p plus p plus p. How many times? N times. So n times p is the mean of the binomial random variable. Why are we studying binomial? Because if we get a good intuition for binomial, there are some other related distributions, probability mass functions like the multinomial or the categorical, which are very useful in things like topic modeling or other interesting applications, for example, in text analytics or even regular structured data, analytics on structured data. Thank you for watching.